All right, my name is Robert Larsen. I was the reporter for Group 3. We did the ejected turbine. All right, so this is how the presentation is going to go. We're going to have the introduction overview, the apparatus, like in other words, how the engine is configured, the theory behind the experiment, the procedure, and then the results. So the way the engine works is gas or air is the working fluid. It comes in through the compressor.
I don't know how you know that.
The gas comes into the compressor, it gets compressed. As it gets compressed, the temperature increases. And then here it enters the combustion chamber, which is where the fuel is mixed in. And then it's so hot it combusts. It has a spark ignition also. And then it comes out there and goes through the turbine. The turbine, then it spins the turbine, which makes more thrust because a lot of the air also comes through here. And the turbine is coupled to the compressor. So the turbine uses some of its work to run the compressor. So it's like a self-sustaining cycle if you add the fuel. And the way you control the RPM is you control the amount of fuel that goes in and out. And so this is the brake cycles, which used to model the jet engine. So ideally, you want to have no entropy change. So you see 1 to 2 is the compression, and then combustion, and then expansion. And then if it was a closed loop, then it would go back here, but instead this is the thrust, and then this is new air that comes in. All right, and this is just another way to look at it. And here you can see clearly how the turbine is coupled to the compressor. All right, this is just another view. This is actually the one that we used in there. And so you can see mechanically is a real picture how it's coupled. And this is what the combustion chamber looks like and the way it's shaped and everything. It's all in series. It's like all one circle. It's one chamber in a circular formation. So it all comes in like this and it goes out and then some more. So the procedure, we followed the lab instruction manual. It started with, you start the turbine by spinning it with compressed air and giving fuel and having spark, and eventually when it gets up to around 30 or 40,000 RPMs, it can sustain without the compressed air. And so the objective of the experiment was to figure out the efficiency, the mass flow rate, exhaust velocity, and then the thrust. So for the analysis of all the data was collected through different thermocouples and pressure sensors, and we used the computer to record all the information at different RPMs. And here, these are just some of the formulas that we used in the calculations. And so for the exhaust velocity, I was able to use V5 over the mass flow, and then these are just other formulas that were used in calculating the mass flow, the different velocities, efficiencies. And then this is how we calculated the work of the compressor, the heat input. This actually, the heat, it has to do with the fractions of which the heat was. Some of the fuel was burned in the compressor and some in the turbine. Unfortunately, it's a side effect of a real life experiment. And so here you can see at the top, it goes organized by RPM. So the smallest RPM, the largest RPM. And these are the temperature, the thermocouples there. We have the inlet before the compressor. And then this is after the compressor, so it increased the air temperature. And then after the combustion, this was your highest temperature. And then here, this is when it goes into the turbine, and this is when it goes out the exit. And the pressures are the same thing. You can see that the highest pressures are right here, T2 and 3. And then finally at the exit, it's almost the same as, it's close to atmospheric pressure. And this is the fuel burn. You can see the fuel goes a lot. When you go from 40 to 80,000, the fuel almost doubles. And so this is the different temperatures. You can see here, like, you can read the graph, but you can see generally as the RPM increases, the temperature increases. And then the same thing with the pressure. The higher the RPM, the higher the pressure. And it kind of makes sense. And you can see that the inlet pressure and temperature from the last slide, that the inlet pressure temperature has not a lot to do with the RPM. All right, the work from the turbine, the work from the compressor are almost similar. The work from the compressor is negative because when you have to give work to something that you're trying to get work out, we consider that to be negative. And so they're pretty similar. The turbine has a little bit more work output, which is what we And then the thrust calculated, the device has they call it like a thrust meter. Basically, it's just this little lever that moves back and forth, and however much it moves, it's calibrated to be thrust. And it varied a little bit different from the thrust we calculated from the formulas. You can see the measured thrust came out to be higher than the ones we calculated in the formulas. So it went all the way up to only 18 pounds of thrust, where it measured 24, when actually in actuality the machine's rated to go up to 35 pounds, which is very difficult. The guy Uptech said it never even has been able to get that high. And so these are some uncertainties. I used data from other lab sections to see that we have it looks like the chart got a little bit skewed, but these are the standard deviations, and this is the thrust and the mass flow. So you can see the standard deviation is very small, which means our data was very similar to the other labs' data, what we want. So, and the conclusion is these jet engines are used when you want to have a lot of power, a lot of thrust, like in supersonic jets. You don't see like a regular small airplane, like a little Cessna that has like a piston cylinder engine. They only go 200 miles an hour. When you want to go really fast or maybe have a bigger payload, like a passenger jet or even a fighter jet, then you're going to need the gas jet engine. They just cost a lot more. They're a lot harder to operate. So RPM increases, and the percentage of fuel increases to 100%. So in other words, what that's saying is the fuel burned in the combustor, the percentage of fuel burned in the combustor increases with RPM. All right, and these were some references. Does anybody have any questions?